Hello.
Good morning. Hey, I haven't gotten to Powerhouse yet, but I will come over. I might be a few minutes late as I get there.
Oh, you're fine.
How did your things go? Did you finish up okay?
Oh, yes. One of the courses finalized the grade for the submission, and one is still waiting for final exam grade.
But you're done.
Yes.
You're done
Yes.
with
Everything
everything you
is
need to
come.
submit. Great.
Yes.
That's a relief. Hello.
Hi.
Hey, Christina, how are you doing? Oh, I can't hear you.
Let me log in. Or,
No, I can hear you now.
okay.
I don't know what happened. I saw your
I
mouth
didn't hear
moving and
anything.
no sound.
Okay. Well, I'm glad it works now.
How did your interview go?
I haven't heard back from them. I think
Yeah.
they usually take a while, but I think it went well. But I don't really like the position, to be honest.
Oh, yeah.
It's a very new campus. There's only two master courses and one undergrad course right now. And
Oh,
all of them are in management. The position is not in management. So I don't
oh,
know who I would work with. Like, it's a bit. I think
that
maybe
is
in,
kind of
in,
weird.
in 5 or 10 years it might be a good place, but right now I think it's too early.
Hmm. Yeah, so they would be relying on you to build that up.
Yeah, I
Uh,
guess.
well, okay. At least you got an interview. That's
Yeah,
awesome.
it was good practice because it was my first time. So yeah.
Yeah. Yeah, that's good. So one of the things I didn't realize when we moved it to the 13th is that Raidul's not here because he just left today
Okay.
for his holiday or winter break travel. So, and he's one of the people that I most wanted to interact with you. But I'll do my best to try to absorb and then get back to him.
Yeah, and I can also kind of give a quick recap on Wednesday next week.
I
Um,
don't think he's not going to be around for until the end, until
I
next
see.
year.
I see. Okay.
But it's recorded.
Yeah.
I am gonna wait a little bit. Are you over in Europe for the rest of the year? Oh, now your sound has gone again. Or
I don't know what's happening with the sound.
yeah, now I can hear you.
Okay.
It
Hmm.
just is a few times. Are other people having that problem or is it only me?
Okay, so it must be me. Hmm. Yeah, sorry about that. I don't know.
Mm, I don't know. So it sounds like maybe something with your mic because you were faint again and then you came back like right in the middle of when you were speaking.
Hmm.
Okay, well, we should probably get started. I'll just
Okay.
hope that other people show up.
Um, oh
So,
yeah, you wanted to share
and
some details, all right? Yeah.
I was the people that were going to share their news are not here, so too bad they don't get
Um,
to. Yeah, so maybe we'll do it at the end if people come. Yeah, go ahead and get started. And I think Zara's gonna be, a lot of things should be coming together anyway. Um, but yeah, I was hoping there would be more people here to have more of a discussion.
mm. Yeah, so there's multiple objectives to this, I would say. So first, of course, to present the kind of final results now from the work, because every time I presented before, it was more preliminary results. And the other one is that I'm kind of thinking about how to develop my job talk. So I embedded it in my job talk structure. So
Right.
before and afterwards will be some parts about my general research and so on, and some other projects. And then the kind of main part will be the heat pump project. Because I'm kind of debating whether I should include it as a deep dive, whether I should do one deep dive or two deep dives and so on. So that would also be interesting feedback for me to hear how it kind of fits into the overall picture. And if
Okay.
you would say it is suitable for the deep dive for my job talk, essentially.
Okay. I'll try to look at it with that perspective. And then if
Thanks.
I think that people here are maybe not even as senior as you, and so they might not have job talk thoughts, but if as people come on, I'll try to warn them that you're looking for that kind of feedback.
Thank you. And also just generally, if it's like understandable and interesting, I think anyone could kind of comment on that.
Yeah. Go for it.
Let me see if I can get. Still see the slides, right? Yeah. Okay.
Yeah, I'm seeing the presentation side and or size and not your notes.
Okay, perfect. Yeah, so in this picture, you can see quite a few elements of infrastructure systems like PV, EV, like electric vehicles and photovoltaic systems. And we always talk about how much infrastructure and technology investment is required, like grids and how can we make EVs smart, for example. And that's all very relevant for the energy transition. But there's a key part missing from this picture. And what is missing? The humans. So I will add the humans to infrastructure systems because we, as humans, interact with a lot of technologies in our daily lives that then has implications for our infrastructure. And that matters because if we, for example, do not adopt technologies for climate change solutions, they can't have their impact. And then how we interact with those technologies can have a large impact on infrastructure needs as well. And different people interact differently with technologies, and that's also very important to consider. So the key message is the interactions of humans with technologies matter for developing infrastructure systems. And I'll show you why and how we can account for that to develop more sustainable infrastructure systems. So one example is adopting low carbon technologies like heat pumps, for example. They can reduce greenhouse gas emissions substantially, but how can we make people adopt them? So slow adoption of low carbon technologies could be a problem because not everyone is an early adopter and keen on adopting new technologies. Another example is uncontrolled electric vehicle charging because they might require electricity grid reinforcements. But when we manage the charging, we might not need to invest as much in infrastructure. So technology use can strain infrastructure systems. And managing that could be faster and cheaper than building new infrastructure. And another example are digital technologies, like apps for car sharing, for example, and other mobility as a service concepts. And more active travel, such as cycling, for example, can change our mobility behavior, and that in turn can have impacts on our infrastructure systems. So infrastructure systems need to adapt to behavioral change. So therefore, industry leaders and policymakers require insights on those human technology interactions to better inform their decisions. For example, on infrastructure deployment, but also to develop incentives to steer those interactions in a positive direction for the system. So in the literature, we have limited knowledge on the interactions of humans with technologies and the implications of those interactions for infrastructure systems. In existing literature, the focus is mostly on optimal technology control, for example, in the case of electric vehicles, how we can manage the charging. And even if incentives are considered, we usually assume full reaction to incentives, so everybody reacts fully to those incentives. But increasingly, the literature identifies the relevance of humans. So neglecting user behavior can be ineffective and even counterproductive. Behavioral changes are necessary and increasingly recognized to be necessary and at least equally relevant as technical solutions. And model studies tend to overestimate participation compared to empirical evidence. So for example, when we think about demand-side management, where we try to manage the energy consumption, there's a mismatch between what we assume in our modeling to develop the infrastructure systems and the empirical evidence we see in reality, how people change their energy consumption. So we need to recognize those strong interactions between social and technical aspects. So my research vision is to develop sustainable and resilient infrastructure systems in the context of climate change and digitalization. So the specific infrastructure systems I'm looking at are mostly energy and the intersection with transportation. Then another relevant element is industry, because they consume a lot of energy and they rely on transportation systems. And as I've just talked about, the humans and the technologies they interact with, which can have huge implications for infrastructure systems. And all of this is increasingly affected by climate change and digitalization. So the specific research questions I'm tackling with my research are first, how do human technology interactions evolve, including the effects of different interventions and their impacts on infrastructure systems, for example, with technology adoption. Then second, how do infrastructure systems need to be adapted to new industrial energy demands, for example, when we electrify certain industrial processes? And focusing on reducing investment costs. So for example, reducing energy storage needs by managing this industrial energy demand. And lastly, how do future transportation energy infrastructure systems need to be adapted to these new developments to create sustainable and resilient infrastructure systems? And so far, I've mostly focused on climate change mitigation, but I want to expand to climate change adaptation as well. So the key contributions to the field are that I'm connecting physical, digital, and human components of infrastructure systems. So the impacts of climate change and digitalization on infrastructure systems and how the technology and physical components of infrastructure are influenced by humans and industrial activities. Then I'm connecting engineering and social sciences to fully realize the potential of technologies. And I plan to collect a lot of data because we often do not know how humans use technologies and what the potentials of different industries are to change their energy demand, for example. And with digitalization, we also have the opportunity to get more data. What types of methods do I use? I grouped them into two groups. The first one is related to data collection and analysis, because often we don't know how humans interact with technology, and there's always new technologies. And we need to analyze large-scale data that has been collected already and identify factors that matter for technology adoption, for example. And then we can use that data for modeling future scenarios, for instance. So I used stated choice experiments, multinomial logit, mixed logit, and willingness to pay space models, survey design, interviews, field studies, also geospatial data analysis and clustering, and decision tree-based machine learning algorithms and longitudinal data analysis. So then with those insights, we can inform our modeling. I used agent-based modeling mostly and energy systems modeling. And modeling behavior can come with a lot of uncertainty. So also using methods to identify the uncertainty like Monte Carlo simulations, sensitivity analysis, or scenario analysis, and techno-economic modeling more broadly. So after this introduction to my research, the outline of the remaining talk is that we first look a bit deeper into a study on the first research question that I outlined on human technology interactions, specifically about drivers for heat pump adoption. Then the second part is on the third research question on the impacts on infrastructure, specifically looking at demand-side management strategies for electric vehicle charging. And then at the end, I will give a broader overview of my work across the main three research questions that I've mentioned, including an outlook for future work. So let's get into the first one. A key strategy for reducing building emissions is electrification of space heating with heat pumps. And about 75% of the building stock in 2050 is already standing today. So that means retrofitting is very important. And an interesting aspect of heat pumps is that they have high efficiency. That's one of their key benefits. It's called the coefficient of performance. So even for low outdoor temperatures, that's usually above 1. And a regular gas boiler can have like 80 or 90% efficiency. So heat pumps are considered a key solution to decarbonize heating. But the question is, how can we accelerate heat pump adoption? So we have limited knowledge on prior conditions for adopting heat pumps. Existing literature looks at characteristics of households that use heat pumps. I've listed a couple of references here. And we know from those studies that fuel prices seem to matter climate, sociodemographics, and housing characteristics. But we don't know what made households adopt heat pumps, so their prior conditions. So those studies have looked at the characteristics of households that use heat pumps currently, but they have no information about what their characteristics were beforehand to know what prior conditions led them to adopt heat pumps. And that's really important to know because only when we know what makes people adopt heat pumps, we can design effective policies. But to do that, we need longitudinal data. So the research question we are asking in this study is what factors drive heat pump adoption in the US? And especially what can existing data tell us on that question? And we only look at the household sector. So our main data source is the American Housing Survey from 2015, 17, 19, and 2021. And that's a national sample, but it includes 15 metropolitan areas, which I've marked here. And out of this data, we create 4 samples. I've listed the number of data points for each of the samples and weighted, so the number of housing units they are actually representing. And within the sample, the number of heat pump adopters also weighted. So the first one only includes the metropolitan statistical areas. The second one is an even smaller sample because it only includes the homeowners out of that previous sample. And then the same for the national and for the national sample, so that we also have a national owners sample that only includes the housing units that are owned by the occupant. And for the following parts, I will only focus on the MSA sample because it allows us to integrate the spatial features as well that we cannot include for the national samples. selection to figure out what matters for heat pump adoption. We mostly use the American Housing Survey. That is following housing units over time, including the sociodemographics of the occupants of the housing unit, as well as housing characteristics and prior equipment that's installed in the housing unit. Then we include variables for the climate, so heating degree days and cooling degree days, and fuel prices for electricity, gas, and oil, heating oil. And I've also collected policies for heat pump adoption, like loans, grants, and rebates across the states in the US. But it turned out to be very difficult to integrate that as a variable because every state has some sort of support for heat pumps, but the specifics are very different. So it is very difficult to compare them and make a consistent variable out of it. So once we have all these variables, we use hierarchical clustering. So we choose the feature with the highest correlation with the classification variable out of each cluster. And the classification variable is a binary variable of adopting heat pump. So it's 0 if a housing unit does not adopt a heat pump and 1 if it does. And we do a couple of robustness checks for that. So we test different distances between the clusters, and we also run the models with different set of features by choosing the feature with the second highest correlation with the classification variable. That's especially very relevant for the clusters where there are a lot of features with high correlations with the classification variable. So these are all the clusters and the features. I will not go through each of them, but I want you to see that we have 13 clusters of 2 to 4 variables each, and we selected one of them based on the correlation on the classification variable. So now that we've selected all the features that we include, we do the classification with a tree-based algorithm and then determine the feature importance based on that. So we use 2 tree-based algorithms. They are suitable for dealing with imbalanced data, which we have in this case because not as many people have adopted a heat pump as the ones that have not. And the 2 we use are gradient boosting. So that algorithm builds decision trees sequentially, where each tree corrects the errors of the previous ones. So it optimizes a loss function, essentially. And that aims to reduce bias by iteratively improving the model. And then as a robustness check, we also use random forest. Because that works a bit differently, each tree is trained independently in parallel. And then the final classification is determined by a majority voting from all the trees, essentially. And that aims to reduce the variance. So by using both of them, we can capture the bias variance trade-off. We train the models for each of the 4 samples with the hyperparameter tuning. We use a stratified split in train and test data because we have an imbalanced sample. And we also do a robustness check here on testing different splits. Then we use class weights and sample weights because we work with survey data, so we need to include the sample weights. And we use cross-validation for better out-of-sample performance to make sure we don't overfit the model, essentially. And then once we have that, we use 2 different approaches for the feature importance. The first one is called the shop importance. That's essentially comparing the model's predictions with and without a specific feature. So by that, we can tell how important a certain feature is, the one that has been excluded. And again, as a robustness check, we use the permutation importance as well. That works a bit differently. All the features are always included, but one is shuffled randomly to basically break up the relationship between the feature and the classification variable. So That approach is based on the decrease in the model performance, and the SHAP importance is based on the magnitude of the feature attributions. And very briefly, I want to show how to interpret the SHAP values to make sure the results plots are understandable. So the SHAP value indicates how much a feature changes the model's log odds output from the baseline log odds. So this equation shows the log odds for a specific observation. K is the baseline prediction. That's the baseline, the average model output across the training data when no features have any effect, plus the sum of each of the SHAP values for each of the features for a specific observation. And then those log odds outputs from the model can be converted to a probability for the class 1 using the logistic sigmoid function. That's a very typical approach to translate the log odds to a probability. But why I'm showing this is to make clear that the SHAP values are not supposed to be between 0 and 1. Okay, now we look at the results. First, some descriptives. So we can see that most of the heat pump adopters used electricity as heating fuel before they adopted a heat pump. So for each of the years 2017, 19, and 21, you can see that the share of the electricity as heating fuel is very large. Some switched from natural gas, but really most of them from electricity. And when we look at the locations, like the metropolitan areas where they adopted heat pumps, we can see that most of the adoption occurs in warm climates. So this gray part of the bar is Miami. Phoenix is also quite large, and at the top, Atlanta as well. The more recent one is a bit more mixed, but still the warm climates really dominate the adoption. Okay, now when we look at the different features, we see that prior equipment, fuel price, mover, and climate are most important. So first of all, on the left-hand side, you can see the features that are ranked by their overall importance. And the left part shows the mean of the absolute SHAP value across all the observations. So that's the mean absolute impact on the prediction of the model. And on the right-hand side, you see different dots, which represent one observation, each dot. And the colors are reflecting the values of the feature. So for example, if it's a binary variable, high would be 1 and low would be 0. Yeah, and you can see that for the overall importance, electric hot water is the most important one, which is prior equipment. The percentage increase in electricity price, as well as mover and the heating degree days. When we look a bit closer into the most important categorical variables, you can see here on the y-axis the SHAP value again, the impact on the prediction. Again, each dot in this scatter plot is one observation. For the electric water one, and the 0 line would be no impact. And the same for the mover variable. And then we can also look a bit more closely at the continuous features, the two most important ones. So here you can see the percentage increase in electricity price. And there's a trend of like the higher the increase in electricity price, the lower the heat pump adoption. And similarly with the heating degree days. So the colder it gets, the less likely is the heat pump adoption. So overall, the conclusions, we can confirm that climate and fuel prices are among the most important factors. That has been found by previous studies as well. But the new insight is that we could identify some factors that are quite important due to the longitudinal data. So the prior equipment, especially electric hot water that we have found is important. So other types of technology matter for heat pump adoption in contrast to other low carbon technologies like EVs, for example. Like for the EV adoption, rooftop solar might play a role. So those are all kind of co-adoption of low carbon technologies. But for heat pumps, it might be other technologies that matter. And the other one is mover. So the change in occupants could be important for retrofitting. So either the heat pump adoption could be delayed until the next occupant change, or it might be a good opportunity to retrofit when there's a change in occupant. And then we did the same analysis for the 4 different samples that I outlined in the beginning, and we observe only minor differences across those samples. Then on the sociodemographics, they don't matter anymore when we include the prior conditions, things like household income and race. But remember that previous studies in literature have found that they matter. So it could be that once we account for the prior conditions, the sociodemographics become less relevant. Then the impact of heating oil prices on the heat pump adoption, that was also found in previous studies. We could not see that because most of the ones that have adopted a heat pump did not use heating oil before. Yeah, and then we also included the change in uncomfortable cold, which could potentially be due to an equipment break. And that also might not affect the heat pump adoption much, at least not so far. So that's a limitation that we have, that this sample is based on the current heat pump adoption, so still a very early adopter sample. We will move from identifying factors for decision making with empirical data to modeling behavior to be able to make conclusions about future impacts on infrastructure. And we will move from heat pumps to electric vehicles. But I will not actually present this part to save some time for the discussion afterwards. But I would like to briefly go over the last part on the overview of my work across the main 3 research questions. So going back to the research vision with the 3 research questions, I'd like to highlight a couple of past, current, and future work in each of those research questions. So the first one on analyzing the human-technology interactions, I've looked at the attractiveness of vehicle-to-grid car sharing, so combining a new technology on using electric vehicles also for discharging electricity to the grid, not only charging them, with a new mode of transportation with car sharing. And then I've also looked at incentivizing people to charge their electric vehicles differently, because once we have identified which charging strategies would be the best, we need to make people actually align with those charging strategies. Then we are currently working on setting up a pilot project for identifying differences between stated and revealed preferences, because that can be quite different, and we want to look at the participation in controlled electric vehicle charging and see how people actually behave differently from what they've said before. And then future research could relate to changes in decision-making for climate change adaptation. So, for example, how people could protect their homes from increased flooding in different areas, or how they change their mobility behavior due to increased temperatures, for example. And I like to go into a bit more detail for one of those on the attractiveness of vehicle-to-grid car sharing. So we conducted a stated choice experiment looking at those different features to figure out what characteristics of car sharing matter most if it is a vehicle-to-grid car sharing, and how it compares to a regular electric vehicle car sharing. And what we find is that the infrastructure placement is really critical. Because people prefer to just leave their car anywhere, which is called free-floating car sharing, where you are not required to return it at a specific station. And when it's electric vehicles with vehicle-to-grid, it matters which charging station you use. So where you place this specific charging infrastructure matters a lot. So the other option would be that you have depots for your car sharing fleet, but that could be less attractive for the car sharing users. Yeah, and that relates to the second point of the importance of the proximity to available cars. So that's similar, that the station should not be too far away, and the permission to park the car anywhere rather than returning it to a specific station. So the infrastructure planning is very critical to make vehicle-to-grid car sharing attractive. Then the second part is on investigating industrial energy demand. Here, I've looked at vehicle-to-X implementations and challenges, and different configurations of the implementations across different commercial fleets and also residential fleets of electric vehicles. Then another project we're currently working on is the potential of industrial demand-side management. So how could different industries change their energy demand to benefit the energy system as we add more renewable energy? So could they reduce their energy demand at a time when there is very little renewable energy in the grid? And then looking at how this industrial demand-side management could complement energy storage, because the goal of that would be to reduce the costs for energy storage. And potential future work could be to integrate emerging industrial energy demands in a similar way to minimize the required costs for energy storage. So those could be medium and heavy duty electric vehicles, as well as data centers, yeah, and also carbon capture, like direct air carbon capture. And yeah, I would like to give you a couple of more insights on the potential of industrial demand-side management. So here you can see the simulations from our energy systems model that shows the storage state of charge in a system. So this reflects one big storage representing all of the storage in the system, and how it discharges in different scenarios, and how it can be complemented by the demand reduction. So the yellow part is the demand reduction, and the green part is the storage state of charge. And what you can see is that the demand reduction can complement the energy storage. So by using that, we can reduce the required storage capacity in the system, which can then reduce the costs. But the question is whether we can actually supply this demand reduction, like whether that's actually feasible in the system to achieve that. So to get more insights on that, we analyzed the different demand-side management events that would be required in the system. So these are the different durations that the demand would need to be reduced. And you can see that almost all of the events are shorter than 24 hours. So the short events definitely dominate, but there are a couple of events that can last very long, up to over a month. And although those are more rare, they could be very critical for the system, because those might be the ones where we need additional storage, and then we have the problem that we still have to build all the additional storage. And then we conducted some surveys with different industrial facilities to see how much they could actually reduce their demand. And this shows a couple of different industrial facilities and their maximum demand reduction in percentage for different durations. And you can see that it varies very much, even within the same industries, like cement 1 and cement 2, and pulp and paper 1 and 2 are very different capabilities. And the shorter durations seem to be easier to implement, like they can reduce their demand more for the shorter durations than for the longer durations. So that's something we want to go into a bit deeper and see what are the factors that that influence why certain facilities can reduce their demand more than others. And then on the last research question on the impacts on infrastructure systems. So I've done a lot of work on electric vehicle integration, and I want to combine that with heat pump integration, because both are new electrical loads that need to be met by the grid, and both can challenge the grid. And then distribution grids, like the lowest level of the electric grid, can also be very different. So the value of demand-side management might vary a lot across different distribution grid types, and we want to look into that as well. And then for future work, I want to integrate those human technology interactions more into cross-sectoral energy models. So once we've figured out some of these interactions between humans and technologies, how can we implement those in different modeling approaches? And another future work is the potential of future infrastructure hubs serving multiple sectors. For example, ports, because in ports, a lot of different energy and transportation factors come together. They could be connected to offshore wind farms, for example, and that could be related to decarbonizing shipping with hydrogen or ammonia that could be produced with the renewable electricity from the offshore wind farms. And then a lot of heavy-duty transportation starts at ports as well, so there could be charging stations for electric trucks as well. So I'd like to give you some insights on the combination of heat pump and electric vehicle integration as well. So here you can see some empirical data on different distribution grid loads, like just the baseline loads as it is today. And you can see that that varies quite a bit. For example, that could come from different building types, urban, rural areas, or different climates and weather conditions. And then when we look at the electricity demand coming from heat pumps and electric vehicles, you can see that they align with during the evening periods. So the brown one are the EVs and the baseline load. The yellow one is just the baseline load, and the green one is the heating with the baseline load, and the gray one is the total. So they do increase the overall peak in the gray areas. And then when we zoom in a little bit, because this first one is across several years, when we zoom in a little bit, we can see that during the evening periods, they do overlap, and the evening peaks are mostly driven by the EVs. And then when we look into one day, we can see that the heating peak could be even higher than the EV peak in the morning, but the overall peak is still larger in the evening because they coincide in the evening. Yeah, and I'll skip that one to make sure we have some time for discussion. Yeah. To finish up, the implications of that work are that we could increase the speed of the sustainability transitions by figuring out how people adopt technologies, and then we can incentivize appropriately. We can develop resilient, adaptive, and just systems, because when we know how humans respond to change, we can make systems more resilient to disruptions and adapt to new decision-making due to climate change, for example. And we can potentially reduce costs, emissions, and damage from climate change, for example. So when we look at demand-side management of the different energy consumptions, we might need to build less infrastructure, like energy storage, which reduces costs. We can integrate more renewables, which reduces emissions, and we can adapt to climate change, which reduces the damage. And all of this because we integrate the humans. Yeah, thank you all.
Hey, thanks, Christina. Wow, you covered a lot of ground.
Yes, and it might be a bit too much, right? I don't know. I'm curious what you think.
Yeah, so I've taken a lot of notes here,
Mhm.
which are scribbled on a piece of paper. I think what I want to do is maybe schedule 30 minutes with you later to go over that and leave the rest of the time for other people to comment.
Yeah, that sounds great. Thank you.
So anyone? And if you feel like, hey, I don't understand this, this isn't my thing, I can't comment, you are exactly like the rest of the search committee.
Do we want job talk comments or just like general question comments? Does that make sense?
All of it. Maybe what's
All of it, yeah.
what's easier to write down and send me in an email afterwards, we can skip, and maybe what's more of a discussion part we could do now. And also, I'm happy to get comments on the heat pump work if that's most interesting to you. Like, it doesn't have to be only job talk comments. Like, yeah, whatever.
Yeah, I think we did want to originally have this presentation so that people could gain that information. So,
Yes.
but I think it's wide open.
Well, just to get the discussion going, I'll ask a question. How about that? So one of the things like that stood out to me is as you were talking about your presentation, you were talking about like we have these technologies and conditions that drive outcomes rather than like the demographic characteristics. Do you see those as independent?
Demographic characteristics as
Are those independent from prior conditions or
from the heat pump work, you mean now?
yeah, yeah,
Yeah,
within that
yeah.
project.
I do think they are independent. Like they might be um, to some extent related, but since we made sure that the features we include are independent, right? Like we did this clustering to make sure the features are independent. Those sociodemographics that we did include should be independent from the prior equipment characteristics that we included. Yeah.
To me, there's a gap there. Like if you're trying to tell a story that like people are part of the system,
Hmm.
in some way that's going back to this is just a technical system.
I see.
And I'd be
Yeah,
really careful about that.
yeah,
Because I don't know that that finding, and maybe that is your finding, but I'm not sure it squares with your larger story.
yeah, yeah, that's actually a very good point. Hmm.
I was interested in that too. Like there were on the heat pump work, there were prior findings that you did not replicate or that you found not to be important. And it's kind of a strong statement saying we found those aren't important. And then I think with there was one like the heating oil price where you said people weren't switching
Hmm.
from heating oil, but is that to what extent is that part of the American Housing Survey is are these people potentially not so well sampled? I'm not asking my question well. So imagine this, you have a small number of people who are heavily impacted by a change or whom a change could benefit or really harm. But because of the sampling methodology and the need to observe the people who have changed, you're not going to see very many of those. And so and then because you don't see many of them, you may not get statistical significance. Um, and so I guess I'm wondering about the power of the longitudinal method or its limitations in identifying important or highly impacted but small fraction of the population people. Do you have a thought on that?
Yeah. So one thing is that the sample should be representative. But there's very few that adopted heat pumps overall compared to the full sample. And then within that, even fewer that adopted it and used heating oil beforehand.
Right.
Yeah, so that's kind of just an observation based on the descriptives. So that kind of, because the
Oh, you're
assumption
cutting out again.
oh, so when you include the heating oil price, you assume that they used heating oil before, and because the price changed, they switched to a heat pump or not. But since they have not used, just based on the descriptives, the heating oil, that kind of assumption already doesn't hold, right?
Mm-hmm.
Yeah.
Yeah, so I guess my question, which I'm not asking very well, is how can you tell if heating oil price is or is not a driver versus the sampling methodology could not or left you unable to distinguish it? Does that make sense?
Yeah. Um,
I'm not critiquing the sampling methodology
yeah.
because you're right that the way they do that is to get a representative sample. But that therefore means that you're not specifically looking at those tails.
I think the limitation here is that the ones that have used heating oil before and then switched, but we can't make a conclusion on that yet because there are not many people doing that. So it's kind of like in that sample, the heating oil price doesn't matter because they didn't use heating oil before. But once we have more people that used heating oil before, it might matter. So I guess the conclusion should rather be that we cannot tell at this point that it matters, which is still different from what the literature says because they say it does matter. Right, yeah, but that's a good point. So we can't actually really say it does not matter. We just cannot say if it matters or not, basically.
Right,
At
you're
least for the current sample, it doesn't matter. Yeah.
in the current sample, you may not have the power to detect that influence.
Mm-hmm.
People who are watching who are maybe not as familiar with the stuff, do you have any comments from just how you experienced the talk in terms of like, were you able to understand it as a person with some technical background? And again, that's likely your search committee, right? They have no clue what you're doing. They probably know this is a little bit important, but what they want to know is, are they hiring somebody who's working on something important, who knows how to communicate it, and who has promising methods of discovery within that field?
What type of department is it potentially?
Most of them are civil engineering, but some are more interdisciplinary of like natural resources and stuff like that, or sustainability more broadly, but mostly technical audience like engineering. Yeah.
Course, I think the storytelling was great. Like it was logical. I mean, Starbucks. I'm really loud. Sorry. But I think the like how you presented it was very logical and like this is what you did, this background, and then for me. I think there was one small tiny thing is the chart of the temperatures, like the cities. I think it would help if you put like just these two colors or a gradient of colors of red and blue, like colder cities are blue and then hotter cities are red. And so that way you can visually see that delineation of like, these are the hotter cities. It was very hard to see that, but it's a visual thing.
Yeah. Yeah, that makes sense. Thank you.
Can I make a comment about that graph too? I think it's a little biasing in its presentation because it's
You want to
a
pull that up,
cumulative.
Christina,
Yes.
so
Okay.
everyone can look at it. Go ahead, Brian.
It's a cumulative area plot, and like when we look at it, like because of that, it's hard to see counts of heat pumps change over time. It just shows us what areas people are installing heat pumps. So like if you look at that N of adopted, that's a tripling. So that's like your number of heat pumps adopted has tripled. And so those bars look like, oh, we have some more adoption going on. But like even your hot climate heat pump, if we interpret that right, has doubled almost there because the cumulative area in that third bar is like 3 times as high. And so I think if you make that just a normal bar chart and allow those to scale, what you're going to show is, look, this isn't just people adopting cold climate heat pumps over this period. It's people in cold climates are now adopting them, and people in warm climates are still adopting them. And I think that's a very different interpretation than you provided.
Yeah. Yeah, that makes a lot of sense. Yeah, so warm climates plus cold ones, yeah. Yeah, thank you.
Just to comment on this, on your findings that were on the next slide, I think that the prior equipment is still standing compared to your previous work, but I thought you had seen a difference between MSAs that you couldn't explain, and I don't see that anymore. Is that?
Was still the issue with these huge impacts of the price, right? Because we could not include the price in the national sample because we don't know where people are. And the prices by state. Yeah, that was just capturing a lot of things. So by using the percentage increase in electricity price, we're kind of still
Interesting. I
covering
see.
but yeah.
It feels like it's more explanatory now than it used to be. Is that?
Yes. Yeah.
Because before it was like, well, it is just if you happen to be in this one place, but we don't know why. So
Yeah.
that's really an interesting step forward in what you've done.
Mhm.
Can I ask a clarifying question about this one too? Is
Yeah,
that allowed?
of course. Yeah.
Why? So the electric hot water heater, is that bimodal because no is predicting a decreased value and yes is predicting an increased value?
Yes.
One thing to think about in like interpreting your results, I don't know why you would have an electric hot water heater in the US unless you didn't have a gas service whatsoever. And like I'm not sure it's the hot water heater driving so much as like what are like what are the actual characteristics of these homes?
Like what?
Because like electrical hot water heating is really, really expensive compared to gas hot water heating. Anybody who has a gas service is going to use a gas water heater unless they're like weirdly climate conscious or something and would like to pay an extra $500 a year. But all of your other data says that they should never do that. And so like I think that's one area where like if I saw this in a job talk, I would want you to go that next step of thinking, well, why am I seeing this result? Because that's how you show us that like you can take your modeling and you're clearly a really good modeler, but then connect it through to like what is the story here? I think that's one area where like you have some really interesting findings, and I would spend more time like thinking, what does this actually mean, and less time showing us additional projects. Because like realistically, I can only hold on to one story in my head and everything else goes out the window. And then I show up and I make a recommendation to the committee based on the story I remember. So like just tell the simple story and like show us that like you're not just a modeler, but you're like a really good thinker. Because like when we ask you questions about this, you respond wonderfully. So
Yeah, thanks. That's very helpful.
That was my thought too, Ryan, is that that's an infrastructure indicator. But like we can't confirm that maybe, but thinking about what we're trying to do moving forward in Illinois, these are all things that could potentially be interpreted, right? Anyway,
Yeah.
we are at
Good.
time, people. Go ahead, Ryan. You can
Oh,
have
I
a
was going
last.
to say, I have a colleague who always says, we're doctors of philosophy. That means we get to think about why we found what we found. And like, if you don't do that, she'll be like, absolutely not. We can't hire that person. And so like, sometimes that does mean like you go outside of what you know and you say, hey, I don't have evidence, but this is what I think is going on here.
Yeah, that's very cool. Thank you.
Okay. You there? Yeah. Christina, I'm gonna ping you and try to schedule 30 minutes with you sometime next week to go over sort of from a job talk perspective.
Yeah, thank you very much.
And yeah, thank you everyone for listening.
Cool stuff.
Thanks.
Yeah, thanks. And if you have any further comments or something, just send me an email.
Yeah, I'm going to
Okay.
email you some job talk stuff because I have to watch a lot of them. So
Thank
Yeah.
you. Yeah. Great. Yeah. Awesome. Okay.
Okay, Sarah, I'll be over there really soon.
Thank you. Thank
Okay,
you,
bye-bye.
Kristen.
Thanks. Bye.